Nicola works for Philips, and for those zooming in from elsewhere, Philips is a company that has been very important to the history of Eindhoven. He's also assistant professor at the university here, TUE, and he will be telling us about doing analysis for MRI scans. So please, Nicola, the floor is all yours.
Okay, thank you so much for the introduction. In this talk, I want to guide you through the work that we have done in the fastMRI challenge, which was aimed at accelerating MRI scans. So the talk will be divided in two parts. First, I want to give you, let's say, kind of a general overview of AI. I guess I've seen several talks on that, so I will not dive too deep, but I just want to give you a flavor of how it can mean in healthcare. And after that, I will talk about the fastMRI challenge and present the work done with the Philips and LUMC team that actually won the fastMRI challenge. So you already introduced me. This is roughly about myself. So I'm a computer scientist by training. I had experience in the startup world, working on 3D scanners. I did my PhD here in the Netherlands, in Delft, working on the analysis of very, very large, high-dimensional data. As part of that, I also worked at Google AI on the analysis of deep learning models, and also at the INRIA, the Research Institute for Computer Science in France. And now I'm a senior scientist in Philips and also assistant professor at TUE, part-time. So maybe just one thing about Philips. So you may know Philips for the light bulbs or the TVs. Actually, the company in the last decade is actually transitioning to be a leader in the healthcare domain. So a really focused company on supporting a healthcare application, and that's, of course, that's what I'm gonna talk about today. Then another real bird eye view on artificial intelligence. So we hear a lot about artificial intelligence these days, and it actually is nowadays covering so much. Basically, also advanced algorithms are called artificial intelligence. What I'm gonna talk about is machine learning, which is a subset of artificial intelligence technology that's really learn from data some specific functionality. So really data-driven learning, which is actually quite fitting for today, by the way. And within this superset of techniques, I'm going to talk about deep learning, which basically is one of these groundbreaking innovation of the, let's say, last decade, where basically the machine learning technologies that are learning from the data are pushed to the limit by learning very rich representation. Now, this is kind of the overview that you often see. What I'm actually gonna talk about, and I'm gonna present one of them, is, let's say, a niche that is not really well known, is actually starting, let's say, from it's 2 years that are actually kind of becoming more and more viable. Those are the some sort of hybrid models. And hybrid models incorporate deep learning solution with, let's say, you can say more traditional computations that may be physically informed models or other kind of traditional computations to really take out the max possible value from deep learning. Okay, so that's kind of to paint the landscape. Now, about artificial intelligence in the healthcare domain. So in 2016, end of 2016, there was kind of a fuss when one of the, let's say, the founding fathers of the modern deep learning revolution, Geoffrey Hinton, actually said, well, I think that if you work as a radiologist, you are like Willy Coyote in the cartoon. You're already over the edge of the cliff, but you haven't yet looked down. There's no ground underneath. People should stop training radiologists now. It's just completely obvious that in 5 years, deep learning is going to do better than radiologists. Now, that actually, I mean, we are at the end of 2020, that we don't see that. And also other people are said that just AI will do everything. That's really not happening. And what we see instead is that there's probably a better quote is, will AI replace radiologists? The answer is no, that's not happening and is not gonna happen. But radiologists that use AI will replace those that don't, because we see really AI as a way to empower people that are already working in the radiology department to just do their job better. In healthcare, we have also a burnout problem. So they have a lot of work to do, and they are focusing on stuff that is not really important, like compiling reports and so on. And in that case, AI can help. Okay, so this is kind of, again, overview. We see a lot of value on the AI, especially in the radiology department, which is basically, as I was showing here, really the radiologist looking at the images, looking at the final outcome, which is actually obtained by the scanners, medical imaging devices. And actually, this is what I'm gonna focus today. I'm gonna focus on how AI can be used before an image is actually showed to the radiologist, and how AI can boost and improve the performance of these systems. And I've seen you are at the conferences held at ASML. I know that also ASML is working on that. And we see a lot of potential actually in boosting the performance by applying machine learning models and deep learning models in particular. All right. Among these imaging modalities, you can see here there are MRI, CT, X-ray scanners. I'm going to focus to a specific one, and that's the magnetic resonance imaging, or MRI. You see a scanner here on the left. It's one of the very nice imaging modalities because it has very nice properties. So first, it does not have harmful radiation for the patient. So it's very nice. You can take as many MRI in your lifetime without having any issues compared, for example, to X-rays. And moreover, compared to the other modalities, it also has a very nice definition of the images. So you can really see also the soft tissue that usually you cannot see in an X-ray. Now, there are some problems though, and the problems are related to the length of the exam. That means that compared to an X-ray that takes a few seconds, maximum few minutes, an MR exam can take up to 1 hour. And as you can see on the image on the left, is not the most comfortable experience. You are in a very small setting, in a very uncomfortable position. And it's also extremely noisy. It's crazy noisy in there. So yeah, any way that can reduce the examination can be very, very helpful. Especially because if the patient moves, there is most likely we have to retake the exam. So yeah, that's kind of the setting. Of course, there have been a lot of technologies that try to accelerate MR and in the last 20 years. But we know that AI will play a role here. And that's also demonstrated by the fact that 2 years ago, a collaboration between NYU Langone Health and Facebook AI Research, they released the first large-scale data set of MR images together with the raw data, what the scanner acquired, in order to accelerate the innovation there. And yeah, so they basically released that and they asked the community, please create the best possible algorithms innovating this domain. And actually to make it even more compelling to work on that, they organized the first fastMRI challenge. So they took some the raw data. You can see it here on the top left. I'm not going to the details. I'll talk a bit more later. They kept that, and also the corresponding images. Then they released a version where the raw data was actually subsampled, so they didn't release everything. That means that you cannot directly reconstruct the images. You will have some artifacts. And they asked the participants to develop an algorithm that can do this reconstruction and provide the reconstruction back to the organizers. And then a panel of radiologists was looking at the difference and evaluating them based on the diagnostic quality or the presence of artifacts, really by looking at the images. And based on that, they decided the winner of the challenge, really based on the observation, the value that can bring to the practice. Now, we participated as Philips with two teams. One, a collaboration between Philips and LUMC, and another one between a collaboration between Philips and several institutions based in Amsterdam. So that was pretty exciting to work in such a high-profile initiative. The most exciting thing was actually that we won all the challenge tracks. So one of the team won the single column, let's say it's one that is a slightly easier task, and one the multi-column that actually really mimics the scanner behavior. So we had actually a very nice exposure to our C-level management. We presented at the top AI conference our solution, which is NeurIPS. And also, I would like to mention that actually we competed directly against competitors, like other companies like United Imaging and Hyperfine, as well as world-leading research labs. So that's already, I'm already telling you the outcome of the challenge. Now, I want to go a bit more technical, so otherwise I'm just talking too much high level, and I want to inspire you a bit on this topic of hybrid models. Describing a bit more in details the model developed in the Philips and LUMC team, and a bit on the model design, how we trained, and the outcome. So in order to do so, let's really have a closer look at how the reconstructions are performed. So in MR, we acquire something that is called K-space. And it looks like that. So it's really, you can see them as a radio frequency signals that are coming from the device. And in the easiest way to think about it is that it's just an inverse Fourier transform, the Fourier domain of your image. It's way more complicated than that, but yeah, it's kind of give you the right mindset if you think about it like this. And so that means, again, if you have the K-space, you do an inverse Fourier transform and you get your image out. As I said before, in order to accelerate MR, what you do is not to accelerate the acquisition of the K-space because there is physical and physiological limits to that. What you do, you acquire less. Basically, you only acquire the lines on this sampling mask. So you acquire less data. But the problem is that if you do that, and you just do the inverse Fourier transform, you get the image on the right. So the one with a lot of artifacts. So the solution is actually to have these hybrid AI or hybrid algorithms to actually go back to the true reconstruction. So again, we cannot just accelerate hardware with the hardware. So we reach the limit there. We cannot go beyond that due to the physical properties of the acquisition system. We need to use software to boost it. And so what we did, we developed the adaptive CS network. That is a deep learning solution that integrates elements of the compressed sensing theory. I will try to give you an idea of what it's about. But again, we integrate deep learning with traditional computations. And what is compressed sensing? Compressed sensing is a technique introduced 15 years ago. It works like that. It's an iterative algorithm. So that means that you don't have just the bad image and the final image at the end. You have you actually improve the image iteratively. So you have a lot of intermediate steps. In this case, you only see one. And what you do, you basically take your image, you apply some function, which is called a sparsifying transform. In this case, it's this f. Then in this domain, you see this in iteration, and you see what it looks like. In this case, is a wavelet decomposition. You apply some thresholding, so basically you put the pixels that are almost black, you put them to 0, or you make them black, and then you just go back. You invert the initial function. So again, you apply a function, you go in this domain that you see at the center, which is the wavelet decomposition. You threshold it, and you just go back. So, and you do that a number of times. So that's the traditional approach. What we did actually was combining the traditional approach, what I just showed, with the AI. And basically, what you think about deep learning and AI is basically the way I think, at least, and I think it's a very powerful way to think about this kind of stuff, is that a deep learning model is nothing more than a functional approximation. And here you see our model, at least from a very bird's eye view. Our model is a composition of a number of deep learning blocks, and each one of these deep learning blocks looks like this. So you have your X, in this case, is the image. You apply one function, the f that I said before, another function, the thresholding function, and the inversion of that function again. Now, what we did was instead of having the hard-coded transformations, we learned them with a deep learning approach. Now, what we did also was use a kind of what is called in the domain residual learning, is a very powerful way of stabilizing the learning. Plus, we computed some functions that were not possible to compute with a learning solution, like with a deep learning module. We compute them as an external input, and then we provide it as input. Now, all the model is fully trainable, so that means also relating back to the work I have presented before. In general, it's a great thing that NVIDIA and all the AI toolkits are actually supporting hybrid computations. That's really is pushing the boundary of the research because we can integrate, let's say, Fourier transforms into the model and so on. Now, yeah, so here to go a bit more into the details, now it's becoming a bit technical. I just want to mention for those of you that are actually working on the field, the F function, so again, the sparsifying transform, the thresholding and the inversion are actually implemented like a similar of unit design. So if you are familiar with that, it's basically an architecture that looks like this, where basically the first part corresponds to the inversion, and then we have going back from the image from this sparsified space, and plus we have something that we added, which is this thresholding. Now, okay, this is maybe a bit technical, but one thing that I would like to mention is that actually we achieved great results just by sticking to very basic deep learning operations. So in literature nowadays, you are overwhelmed by a lot of different architectures, a lot of different computations. We, by design, stick to a very simple one because we knew that we can control and we can inject in a much bigger framework. And so that was a very powerful idea, and it works like a charm. Okay, now I presented the architecture. For some of you, it resonated better than for others, but okay, that's kind of the flavor. But I think another thing that you see in the AI literature is that people tend to focus a lot, at least maybe outside also the pure machine learning research community, is that people tend to focus a lot on architecture and try a lot of different architectures, but actually, one important point is actually the definition of the loss function, because as I say, the loss function, so if a deep neural network is or a deep learning model is a racing car, the loss function is the driver, and power is nothing without control. So you really need to have the right loss function to drive your network. And in the collaboration with LUMC, we focus on the exploration of a lot of loss functions. And that was, I mean, I think this is actually not all of them. We actually explore a bit more, a lot of combination of them, more advanced one and a more simpler one. But we really do a thorough analysis. And the most important lesson there was actually that these numbers do not actually capture the real true quality of the resulting images. So for us, it was extremely important not to just validate them on numbers, like on these tables here, where you see a lot of different losses with the corresponding, let's say, quality metrics. And we had actually quite some of these quality metrics. It's actually more important to just generate the images and just look at them to get the flavor of the resulting image quality. That was really important. We showed that to radiologists, and that was a super important feedback that we got. Yeah, I think in view of time, I will not go too much in details in the one that we have chosen. But yeah, okay. So it's called multi-scale SSIM, and it was designed to mimic the perceptual behavior, the perceptual system of humans, in such a way that artifacts at different scales are weighted equally. So here on the right, you see, for example, an image with different, basically degradation, different frequencies. And basically a number of people were asked to grade, to find at which level of artifact it was the same. So in this case, the red boxes correspond to that. And yeah, so that's really to, again, the focus of putting the human in the loop. Actually, this is my focus at TUE as well. I'm really interested in focusing our machine learning model in such a way that can help us directly and not just output a number that maybe is not controlled and we cannot really rely on. And on top of that, we actually adopted a mixed approach because for optimization reasons, it's much easier to achieve better results. Now that's the piece on the loss function. Again, it's super important if you work in machine learning, please focus on it quite substantially. I don't see it too often around, but that's super important. Now, about the training. So again, also another trend that we didn't follow in machine learning is we want to have a model that rules it all, right? So that one single model works for everything. At the same time, for the challenge, we observed that there were two very different looking images in the challenges. And you can see them here. One, let's say the bright one and the dark one. And they had different undersampling rate, different protocols, which I just said, the bright and dark, they are called protocols. And also they are acquired with two different systems. Now, a way to train will be to train for all of them so that we have a model that works for all of them, which is feasible. But in the challenge, we were focused on getting the best possible result. So what we did instead was to train one single model that can work for everything. And then we fine-tuned this model several times on the more specific subpopulations. So again, so we took the model, fine-tuned on the different accelerations that we were supposed to focus on, and then for the different scanners and different output. Now, this is again another powerful concept. Again, I'm not giving the details here, but in general, if you do machine learning, that's a powerful concept. You can start from a model that works very well in general, and then you can make it super optimized for some specific working conditions. All right, so that's kind of the overview of the design philosophy, loss function, and training strategy. Let's have a look at some results because, of course, those are more insightful. Here you see on the left, actually what we would get if we do the traditional reconstruction. You can see it's basically, well, you hardly see actually a knee there. On the right, you see the ground truth, while at the center, you see the reconstruction. Now, the reconstruction is not optimal. This is something that by no means is going to be used in clinical practice. But if you compare it with what we start with, it's really, it's really day and night. And we can achieve that, not in this case, I have to say, partially because of the AI, but the main focus here, if you look also at our competitors, was really to integrate this hybrid computation, such that the data that we acquire are actually dominating the AI part. Again, so this is really pushing the boundary, is not going to be used. But if we look at, this is another example, very extreme, for again a different, for a very challenging reconstruction. This one looks already slightly better. Again, will not be used on, let's say, the very tricky scans, but in general can be open up new application actually. Again, this one actually is for an acceleration of 4. Here you can see a bit better. The results are actually getting quite good at this point in time. You can see nicely also defined structure at the center, and that's rather good. If we go to another another acquisition that is less noisy, already with a high acceleration of 8, the recon looks quite good. This is quite good, and it can accelerate the reconstruction up to a factor of 8. So reduce the time that you spend in the scanner by a factor of 8. Well, if you reduce by a factor of, we go to less than 4, basically you can hardly tell any difference between the reconstruction and the ground truth, which is, pretty good, because we know that we can directly have an impact on people getting a scan. And that brings me to the conclusions, where we won and co-won the 2 most challenging tracks. Improvement over the compressed sensing theory, I think it's within reach. Importance of designing the loss function and evaluated with people directly looking at it, and also the importance of combining prior knowledge, which is in this case MR physics, but in general, I mean, every physically inspired model is getting traction, and I think it's the future. So that's pretty cool demonstration of that, I would say, this challenge. And let me just conclude by saying that I'm here presenting for the team, but again, the team was extremely talented people. It was very inspiring to work with them, and that brings me to the end of the talk, and I'm happy to answer any question.
Yes, thank you very much, Nicola, for this amazing talk. So we do have a couple of interesting questions from the audience. So to start with the first question from Ektiar. Well, it's great to be in such a competition. From a team building perspective, what do you think gave you the edge in terms of profile of different people inside the team for winning the competition?
I like this so much. Actually, so we had the main focus when we built the team was really to have people with different but complementary skills. So I'm purely, let's say, a machine learning and data analysis person. Actually, when I started, I had very limited MR knowledge. We had people deeply in the MR side with limited machine learning knowledge. We had people from LUMC without machine learning and without MR knowledge, but with let's say the radiology side, they know what to look for. And so really the combination was boosting the performance, incredibly.
Okay, cool, super interesting. And then another question from Ananina. Will this be implemented within the clinic?
Absolutely, that's of course our goal. So I mean, the challenge was good, but for Philips in general, the main focus is on the improving the life of the patients. So of course that's the angle. We have to see when we will get there, but as a research, we always strive to get to the clinic. Yes.
And then another question from Actier. Do you have any intentions of posting a challenge on Kaggle yourself?
Sorry, on?
On Kaggle, the
on Kaggle.
competition platform.
Yeah, actually, no, ourselves not really, but there is a new challenge from the organizers, the NYU and Facebook. They already organized the second challenge, and actually they want in the future also to expand to their data set. Maybe it's funny to say that all the fastMRI data was on data from our competitor with Siemens. And so it was great actually to win on their data. But of course, they are aiming actually have a multi-vendor data set in the future.
Yes, and then last question from my side. So you discussed it's really important to involve the radiologist in designing the loss function. How do you feel about the fact that it might be from a literature and academic perspective, it might be an incentive to go for the benchmarks that are out there, just to get your publications out there more easily. Well, of course, this might be a little bit the opposite of doing a new research and coming up with your own designed loss function based on the radiologist input, because it kind of makes it from a research perspective maybe a little bit subjective on exactly what kind of loss function you choose based on human input. Yeah,
that's. I'm really passionate about this. What you can see is that the machine learning community is super focused on the numbers. They just want the numbers. Sometimes I have collaborations where people just want to look at the numbers. They never look at the resulting images. And I can understand that from a machine learning point of view. I think really to have a, let's say, from a practical point of view, those that will really have an impact in the field in general, but they really go beyond that. They try to understand when the loss, well, let's say the metrics are not really fitting the task that we have to solve. Because there is this idea that the metrics are everything, but the metrics are not capturing the true meaning, what we really want to achieve. And one thing to say is that we didn't encode the radiologist as a metric. We just worked with our metrics and presented the results, and then still use existing metrics. But we selected them based on the human input or taste. I'm not sure if it's clear. It's a complicated topic.
Yeah, I think it's quite clear. So you kind of try to bridge the worlds in that sense, still give the metrics right, but as like a final call involve the radiologist to actually have an open discussion on what the right metrics will be in the first place.
Yeah, correct. Yeah. And maybe another side note, in the challenge there were two phases. In the first one, let's say the top 5 were selected based on the metric. And then the final winners were selected based on the radiologist input. And what you could see that in some of the tracks, actually the winners of the radiologist feedback were actually not the winner in the metrics. So that's really a clear demonstration of that.
Yeah. So would you consider having these kind of contests a good way of bridging this gap?
Absolutely. I think absolutely, yes. It's
okay,
also quite healthy for the community.